to move on to something else, but I'll do it real quickly. This chapter is actually a step above what most good chemistry students could do. If you're really good at this chapter, you're going to be good at a lot of things in chemistry. This is a lot of chemistry involves solutions and ions and stuff like that. We talked about how the nerves work, muscles work. There's a lot of things that are driven by ions, concentration of ions, and that kind of thing. And that's what this chapter is about. So try to take it a little more seriously. It said, if I really want to do well and I'm thinking about some kind of science field, I want to try to excel in this chapter. One thing that was a problem, two things are a problem here. Don't forget that the word concentration is a ratio. So it has 2 units, and also you can get fooled. Watch right here. Let's say I knew the concentration of this right here. What would the concentration, hang on, let me get a pin out. Okay, so look at this right here. Which one of these is most concentrated? Which one of these is most concentrated? C. And so you understand that. It's kind of like density, isn't it? Yeah. But watch. Here's where a lot of you get fooled. Which one is more concentrated? This much of this or all of that? Which one's more concentrated? This much of that or all of that? Which one's more concentrated?
This much of that, not this.
And so what you need to know is any volume, any amount of that is more concentrated than an ocean full of that. You get that? It's a ratio thing. So we have to watch out for ratios. The next thing is there are many units for concentration. And I'll give a quick story from yesterday. The only time I see this one used is for that graph we will look at later, solubility graph. How many grams of solute will dissolve in 100 grams of water at a certain temperature? And it's such a classic graph, they're not going to get rid of that concentration unit. So you won't use it that often, but they'll use it occasionally. All of these, this one and all of these, have really nothing to do with moles. It has to do strictly like parts per 100. What's another word that says parts per 100? Percent. And then we have parts per 1,000, parts per million, parts per billion, parts per trillion, or even this, percent by volume. Those are all things you can do mathematically, and they don't even involve the mole concept. And so I think today, if you went to college and you went to a biology lab, some of the biology labs are still making their solutions like 10%, 5%, 20% salt. And because, number one, you don't even have to think about chemistry. You just have to think about numbers like that. Now, so why, I mentioned this yesterday, why in the world would somebody say we need to have a new concentration unit, and somebody say, well, wait, the other ones work. Well, yeah, but what if I have 25 milliliters of 15% NaCl? How many moles is that? Well, wait a minute. That's not so easy, is it? If I have 15 milliliters of 5% NaCl, how many moles is that? I'd have to step back and do a lot more math, wouldn't I? So they said, if we use this right here, this new definition, and by the way, look at the definition. It's not per grams of solution. It's per liters of solution. If we use definition molarity equals moles of solute per liters of solution, why would we want to do that? As a matter of fact, even the definition, go ahead.
It makes it really easy to find certain things.
Like what, though?
How many moles of solute.
Right, and we'll talk about all four of these equations, but if this is the equation for molarity, if we rearrange it, then what is molarity times volume in liters? It gives you moles. Well, guess what? Once you're in the mole world, aren't you in the stoichiometry world?
Yes.
Remember that balanced equation? Can I just put that in there? I got my moles already. And that makes it so incredibly easy. So anyway, but it does, unfortunately, it did involve every lab in the world having to buy these expensive things called volumetric flasks. Because if I want to make a let's pretend this is 1 liter. I didn't want to reach all the way up there, but let's pretend this is a 1 liter volumetric flask. If I wanted to make a 1 molar solution of NaCl, I would put a mole of NaCl in there, 58.5 grams, and then how much water? I don't know how much water, but I will tell you, I'm going to make it go up here so the bottom of the meniscus is right on that line. You get that? And how do I know it's not a liter of water? Because the salt took up some of the space, didn't it? So I don't really know how much water's in there. It's close to a liter. It's close to a liter. I'll get it. But anyway, so the definition does require a new piece of equipment there. And molality is a minor thing. We talked about freezing point depression. Remember that? Boiling point elevation. It has to do with how many moles are dissolved, and they call that molality. Yes?
So when you have two miscible solutions, is one of them a solvent? Or is it
Excellent question. Man, excellent question for this early in the morning. If you had a solid and a liquid, normally the liquid is a solvent, all right? And the thing that gets dissolved is called the solute. It would be the salt. But what if you had two liquids? All right, then it would be the greater, whichever one had the greater number of milliliters, that would be the solvent, and the other would be called a solute. I guess if you had even amounts, it'd be hard. I can flip a coin on that. So great question. That's a great question. All right. Anyway, so now what I want to do is I'm going to flip this over, and one thing that I want to get you guys to do, and again, I never did it in high school. I never did it in college. Matter of fact, when I first started teaching, I taught a lot of biology at that time, and even when I taught chemistry, we had this person who had been a chemistry teacher for 25, 30 years, whatever it was, and I was good friends with him, and I said, I want to do this lab here, and I had never been taught to make solutions. So I asked him, he said, sure, I'll make it for you. So guess what? When I first started teaching, I didn't have to make solutions either because somebody else made it for me. Then I got to the point I thought, I need to learn how to do it. Why can't I make my own solutions? As far as the school, let's say I want a lab that uses 0.1 molar NaOH. I can do it. Companies will sell you 0.1 molar in these cute little bottles with a label on it and everything, and they'll charge you about $25 for each one of these bottles. I can buy a whole package of solid sodium hydroxide. I could make 500 of those bottles for about $30. All I have to do is be able to make the solutions. If I know how to make them, I can save the school hundreds and hundreds of dollars just because I can make my own solutions. Yes?
Does that money go to your bank account?
No. Money and power, right?
Yeah.
I save the school. That means I don't have to ask them to buy certain things. So that's how it saves them. So, all right. Well, anyway, I would like you to be, you're going to college, and very few of the people around you would have made solutions. And I want you guys to be able to make solutions. So some of the labs that are coming up, you're going to make your own solutions. I have another one where I'm hoping you can make several solutions. And I'd like you to be able to make any kind of solution. Later, you'll also have to do, remember how we did serial dilutions? In one lab, you'll make a solution that is maybe 0.1 molar, and then you're going to take the test tube and make serial dilutions. And you get 0.1, 0.01, 0.001. See that? And then you can make concentrations however you want. All right, so let's get started here. I'd like you to, did we do this one yesterday?
Yeah.
Do we start it or do we finish it?
40 grams.
Okay,
60 grams.
let's go ahead and sit next to somebody. You can have 2 or 3 people in a group, 2 or 3 people in a group. Write down, number one, I want the actual steps on how to make it. And if you do any kind of math, do that over here. And then actually tell me, step by step, how do I make this solution? And then we're going to move on to the next one, move on to the next one. So my goal is to try to get all these done today. All right, sit with somebody and say, hey, we need to make this. How do we make it?
Oh, and you want to make some solutions with me?
So I want to step by step,
So we're in a group already.
almost like I'm baking a cake. You're going to tell me exactly how to make these.
So the funny thing
You want to make
is,
solutions?
oh well, shoot.
60 because you 5 by 10.
Okay, so
So, did you know? Well, I see you already got your work done.
I think we started this one yesterday, didn't
We
we?
did.
So, 20% by volume, well, it doesn't say how large it wants us to be, so let's just make it 20 and 80.
Okay, then.
600
So,
times 21.
20
That's gonna be.
a half 60. You got sure to work with 80 milliliters of sugar.
Are we doing all of them?
Yeah, I think so. We doing all of them?
Let's do the first two, and we'll stop there for a minute. Let's do the first two. Okay. I left something out. On B, I left something out. We need 800 milliliters. My fault. We need 800 milliliters of this to do a lab.
Not
Just do 0.2.
Yeah, you shouldn't have been able to do number two because I didn't tell you how much.
We just made up.
Oh, you did? Okay.
1600, maybe that's more.
160 milliliters. Yeah. It's 600. You do. Let's do it for the next one. We're waiting for everybody else.
Only if you want to.
So you got a 1 molar solution of NaH.
I really feel bad
Poor Parker.
Poor just everybody, you know, just all pours around.
It's tough week from Aaron Rodgers got COVID, so he's celebrating.
It's so everybody.
Just go through it. We can get through this.
Right?
How was the first practice?
Can we change number D? I'm gonna make it a little harder. Let's do D. Let's make it 0.1 molar. How about that? All right. Let's do the first two. And let's see how well you're doing. All right. On the math, we need 600 grams and 10% by mass. So 10% of that is 60 grams. So you're gonna put 60 grams of NaCl into what kind of container?
Volumetric.
No, we don't need that.
Never mind, I was guess.
We don't need that. As a matter of fact, that's what's neat about it. I think that's why biologists still like it, because I don't need any special glassware. Give me a beaker, give me a bowl, give me whatever, just put it in there. Now, what am I going to do then? After I put 160 grams of NaCl into some kind of container,
540 grams of water on in there.
okay, 540 grams of water, and
Shake it.
stir and enjoy. Yes. Anyway, that was pretty easy, and I think that's why I think some labs still do that, but not the chemistry labs, because they know the mole concept is too important. Now look at the next one. It's the same thing, except I need 800 milliliters. What's 20% by volume? So I would add 160 milliliters of alcohol, and then add 640 milliliters of water. And again, I don't need any kind of special container. And then stir. There you go. And I don't know if I'm enjoying that. Okay. Now, the next one, we can do it by thinking, or we can do it by one of the equations in this chapter. One thing you can do is you can set up the equation molarity equals moles of solute over liters of solution. Okay, now, the total volume is going to be 1 liter, so I'm going to put that right here. And then what is the moles of solution? Well, we know that, we don't know that, but we do know that the molarity is what?
1.
Now, here's something that's kind of neat. I understand you like math, but look at the units.
1 plus
Look at the
1
units. You know it's going to be 1. X is going to be 1, but what? You have no unit. What's your label? It's going to be big M over L. So what is big M over L? Well, what is big M? It's not moles. Big M is not moles,
Molarity.
Malaria.
which is moles per liter
Molarity.
divided by liters. What
Oh.
ends up happening?
Layers
They cancel
out.
and you get moles.
No change.
So my X equals 1 mole. So then what is 1 mole? So what I would do is I would put, what is this, NaOH? 40 grams of NaOH, that's 1 mole. And what would I do with it? Where would I put this? Yes, in a what? 1 liter volumetric flask. Now what? Now what? Anybody? Say, yep. Fill where? Up to where?
100.
Okay, the line. Since we know it's a 1 liter volumetric flask, they have this line here. Now, I don't remember in 10th grade whether you did you guys in 10th grade do the lab where you compared taking a volume with a graduated cylinder, a beaker versus a pipette? You guys, okay, good. When they made this part of the flask skinny, they did it on purpose. They did it skinny. They couldn't make it super skinny because it'd be hard to pour in there, but they want to make it skinnier because then you would have a more pronounced meniscus. And the more pronounced meniscus makes it easier to put the bottom of the meniscus right on that line. So you can't put the top of the meniscus here. You have to make the bottom of the meniscus touch that line. And that's what that company did. They even on the side said, let's see if I can read this here. It says plus or minus 0.2 milliliters. This is a 500 milliliter volumetric flask. If you get on that line, they guarantee it'll be within plus or minus 0.2 milliliters out of 500. And that's pretty good. Okay? And I'm sure you could buy something even more expensive than this if you had to be even more careful on that. All right. So, yeah, fill up to the line, and then, yes.
So earlier you on the right side of the page it says moles per liter.
Right.
Liter. Wouldn't that be moles per liter squared?
Okay, good question. Moles per liter divided by liters over 1, because liters is liter over 1. When you divide by liters over 1, that's the same as multiplying by the reciprocal. Whoops. Sorry. Wait a minute. Hey, good catch. Moles per liter. What did I do wrong here?
Yeah, it would be a liter squared.
No, that's not going to happen.
No.
Keep those thoughts. I'll leave. Okay.
Oh, all right. Well, let
The
me this.
scientists do his thing.
Did you ever see that video that's like, hold up.
Hold
Something ain't right.
Oh.
Something ain't right.
Oh, sorry, my fault. Look what happened. When you rearrange this equation, solve for x, you multiply both sides by liters. My fault. So it's moles, it's molarity times what? Molarity times liters. Okay, so this is moles per liter times liter. Good catch. Thank you very much. So when I do that, I multiply both sides by 1 over liter, and that gives me moles. Excellent, excellent work. All right, now let's do the next one, and see if you can do this one. You may have to use the equation on this and see if it works. All right. Let's do a 0.1 molar solution of NaOH, and let's make. I only need 250 total. So see if you can figure that one out.
Working on
And I made this up, so I don't know the answer, so. Did you end up, did your work show that you needed 0.025 moles? Okay, now what's the fast way, what's the quick way to go to moles, moles to grams? What's the fast way to do moles? If you're in the mole world, what's the fast way to go to grams?
Molar mass.
Yeah, but what do you do with it? Multiply or divide? Okay, so let's take this times 40. All right, so what is that? 4, is it 0.4? Does this come out to be 0.4? What's 40 times 0.025? 1/4, wait, 1/4, wait, 10. Is it 1? Okay, that's all right. So I would need 1 gram of NaOH, and where would I put that? Where would I put the 1 gram of NaOH?
In your little flask.
Which flask?
The
And you wanna
volumetric.
fill it
Yeah,
up.
and not this one, because that's 500, but, so I'm gonna go find a 250 milliliter volumetric flask. I'm gonna put 1 gram, 1.00 grams of NaOH in there, and then put the rest water until I get up to the line, right? Now again, when you guys start making your own, you'll see how you wanna be careful. Like one of your labs, everything depends on whether or not you made your solution right. And so you wanna make sure you watch your partners and say, well, how are we doing this? Let's do a 1 molality problem, and I'm not gonna stress molality, okay? It'll come up in chemistry, but it's not gonna come up that often. The definition of molality is different than molarity. So go find your definition for molality and plug your numbers in and see if you can get this one. All right, sit down with somebody. Let's find it says here, I wanna make a 2 molal solution of sodium nitrate, and I need 3 kilograms altogether. 3 kilograms. Whoops, I just thought about something. We're doing molality, right? I need 3 kilograms, no, wait a minute. I need 3 kilograms of water. There you go. I just thought about this, because this is actually,
Solvent, not solvent.
right, it's not solution, but it's actually solvent. I need to change that. Okay, so get your equation out. Molality equals moles of solute per kilogram of solvent. And again, I think people at one time, molality was kind of neat. At least they stuck the mole thing in there. And then later somebody said, wait a minute, you know, if we didn't, we're still going to have a little trouble getting to into the mole world quickly. So then they had to come up with molarity. That would be a great extra credit project for somebody to say, who's the first person to use molality, and when did molarity come about, and was there any story about the switch over between molarity, that kind of thing?
Back there was.
Could have been, or they could have been completely isolated. One group of people did this, one group of people did that, and this group of people didn't want to change because they were stubborn, and this group of people said, ours is better. So I don't know. Did you know at one time England for a long time, think about the word billion. Billion means 2, doesn't it? By 2 sets of 3 zeros. At one time, 1, 0, 0, 0, 0, 0, 0 was a billion in England. Is that a billion here? Well, it didn't even make sense what we say. Our billion has 3 sets of 3 zeros. But however that happened, England, we were more powerful at that time. England said, we'll switch.
What's billion in there for?
Trillion should be 3 sets of 3 zeros. But what is a trillion here? It's 4 sets.
So where'd million come from?
Where did what?
Where'd million come from?
Okay, that's a good question.
Did they just put it opposite?
They might not have a million. I don't know.
Because milli is,
Maybe they didn't have it. Well,
Milli
milli
is
is
10
1
negative
thousandth.
yeah, that's strange.
Okay, anyway, does everybody get this? All right, so here you put the 2 in for molality, and what units would molality have? Instead of putting a little m, can I write moles per kilogram of solvent? And then equals moles, and we don't know that. That's X. And then 3 kilograms here. Okay, multiply both sides by 3 kilograms, you get 6 moles. I need 6 moles of NaNO3.
Yes.
All right, what's the, did anybody get the molar mass of NaO3 yet? What's the molar mass of, I need 6 moles of it, so what's the molar mass? What's Na? There's no way a second year student shouldn't know. What's the molar mass of sodium? 23. And what about a nitrogen? No,
Oh.
14. Oxygen is 16.
Oxygen 16.
And then
Three.
3
But it's
oxygens,
three.
48.
But it's 3 though.
Right, 48. Okay, so here we go.
Second year student.
31.
Okay.
Dude, I got the
Knew
right.
it all along, guys.
All right, do you have 85? Is it 85? Okay.
It's a whole lot of blank.
So
That's
now
all fluke.
we need 6 moles, and each mole is 85 grams. So 6 times 85, 510.
Yes.
So we're going to add 510 grams of sodium nitrate, and what are we going to add to it?
The 3 kilograms of water.
And what would 3 kilograms of water look like?
That's my CO.
We should do a project one day where we have to find how much a liter of water weighs.
That's funny.
Oh, yeah. Maybe we do that. Well, anyway, so how much is it? So 3 kilograms of water is what? 3 liters. 3 liters of water, isn't it?
That makes sense. That's cool. That's cool. That's cool.
All right, so anyway, you add that to 3 liters, and any kind of container will do, because this is not dependent on, it doesn't say liters of solution or kilograms of solution. Okay, that's enough of that. Now here is the part that every year, some of the best students still get tricked up a little bit here on this, because right now they're kind of relaxed and said, I think I get this. Let's do the next one. If you were to put 50 grams of this into 500 milliliter volumetric flask and add water up to the 500 milliliter line, what is the molarity of this solution? All right, talk to your partner. What is the molarity of this solution?
So there's 50 grams. So 500 milliliters
Finding the mo- I found the molar mass.
of FeCl3. Fe is 56.
55.8.
So 56.
Okay. And then what about Cl?
Cl is 35.4.
Right, 35.5
So 35.5.
times 3.
160.
That's 71 plus.
Wherever he's. Yeah.
You can have 0.308, 3.3086, because you.
Then you gotta divide that by 50 to find how many moles.
What?
So you get
Or
divided by
50
2.
divided by
No,
that.
times it by 2. You times it.
No, that's just the number of moles you have.
All right, what do you think? How many, what's the molar mass of iron 3 chloride?
162.5.
Is everybody getting 162.5?
Yeah. I got 162.3.
Okay, that's fine. I'm fine with that. I'm fine with that. I'm fine with that. Now, be careful here. I'm going to put 50 grams of that. What's the shortcut way of doing grams into moles?
You just do it in your head.
No, remember you just did the divide by molar mass. Okay, so let's do 50 divided by 162.5. So how many moles is that? What do you have?
It's 0.308.
Point what?
308.
Okay, that's moles, right? Now moles of what?
Polarity's 0.6.
But now molarity is not moles, it's moles per. And how many liters is this?
0.5.
Okay, so that's going to double that to 0.716. Right? I mean, 0.616. Is that right? Okay. So anyway, it's going to be what is the concentration of a point? Let's see. What did I say? 0.616 big M. Now, here's where you get fooled. Here, I don't want you to get fooled. Okay? I don't want you to get fooled. But what is the concentration of FeCl3? What do you think, Clayton? What do you think? Yes. What is the concentration of iron 3 ions? So let's try it again. What's the concentration of FeCl3? it is 0.616 big M molar, right? And then what is the concentration of iron ions? Ready? For every one of these, how many of these do you get? So it has to be the same concentration, right? So what's the concentration of iron ions? 0.616. What's your unit? No, not moles. What's big M? Molarity. Remember, molarity is not moles, right? It's moles per liter. Now, what is the concentration of chloride ions? Yes. Anyway, if for every one of these, you get 3 chloride ions, don't you? So you have to multiply this times 3. I'll do it in my head to see. 8, 4. I don't know if I did it right. Is it 1.848? Okay, 1.8. So about 1.85 molar. Now here's a tough one. What's the concentration of total ions? For every one of these, you get how many total ions? 4. So let's multiply this number times 4. And 4. 2.
Let's get rid of the H.
What do you think? So I think that's the one that people kind of mess up on a little bit. You're going to do a lot more with ions in this chapter, and you actually do stoichiometry with this thing called a net ionic equation. So we have to know, if we know the concentration of the whole compound solution here, then we can say what's the concentration of that ion or that ion, and then we can do stoichiometry that way. Hey, that was a great day. I thought you accomplished a lot. We found out a little bit